We're going to learn about the Hertzsprung-Russell diagram, which is a very fancy name for a diagram on page 15 of your Earth Science reference table. Its nickname or shortcut name is the HR diagram, and it just compares temperature and luminosity, which we're going to see what that is shortly, for various stars. So let's take a look at the graph on page 15. Now this looks like a map of outer space with a bunch of stars, but in actuality it's just a graph, and it's particularly or specifically a scatter plot. So it's a scatter plot graph of luminosity versus surface temperature in various stars. And luminosity over here tells you it's the rate at which a star emits energy relative to the sun. So that's just how much energy the star is releasing, and it's comparing it to the sun. So if you have a star that has 100 for luminosity, that means that it emits 100 times more energy than the sun. On the x-axis we have the surface temperature in a unit called Kelvin. Kelvin is unique in that 0 Kelvin actually means absolute zero, where the molecules aren't moving at all. So we're going to be taking a look at this diagram and really trying to figure out what it means. But to start off, it may make more sense if we refer to a scatter plot of height versus weight in people and compare this to the HR diagram. So here is a diagram where we have weight on the x-axis and height on the y. The unique thing about this diagram and the HR is that the lower numbers are on the right for the x-axis, and as you go to the left, the numbers get bigger. So in this scatter plot, we can see that different people have different weights. So we have all the dots representing the height and weight of different people that were measured. And we can see there's a general trend here in the middle that shows you that as the person's height goes up, their weight is higher. So shorter people are lower in weight, medium-sized people are more medium in weight, and again, the tallest people are the heaviest in weight. So we can make a general statement that the taller a person is, the more they weigh. But as you can see, there are some exceptions to this rule. Over here, we have a tall person who is really light in weight. And over here, we have a short person who's very heavy. So there are exceptions to this rule that the taller you are, the heavier that you get, because this person is tall and they don't weigh a lot, and this person is not tall and they do. So the HR diagram has a general rule, but it also has exceptions which are unique and special stars. So back to the HR. The HR diagram shows the relationship that for most stars, as temperature increases, the luminosity increases. And that's called the main sequence stars, which we're going to learn about later, are an early stage of their development. So stars over here are low in temperature, now not low in weight, but low in temperature. And they're not very bright, so they line up with the low part of luminosity. We go over here to these scatter plots, and we can go down here and see they're really high in temperature, and they're also really high in luminosity or energy release or brightness. And of course we have stars in the middle that are going to be medium in terms of temperature, and then therefore medium in terms of brightness. So again, these are our main sequence stars. They're following the main rule or the main relationship. But now there are exceptions. Up here we have stars that are really bright or luminous, the supergiants and the giants. So they're high in the chart, meaning they have a lot of luminosity, but if you look at where the plots are, they fall down here where the temperatures are lower. So that breaks our rule. Usually stars that have a low temperature also are not very bright or not very luminous. And then we have the stars down here, the dwarfs, which, if you look, they're on the left, so that means their temperatures are higher. But even though they're really hot, they're very, very dim. They're not luminous at all. So the stars that fall off the main sequence are exceptions to this relationship, and as we're going to see, they're at different stages of life. So a giant star is an intermediate stage, and a white dwarf is a late stage of a star's development. We also can use this chart to remember that color and temperature are related. So certain stars and certain colors are hotter, and certain ones are colder. So the hot stars are blue in color and have very short wavelength energy, compared to the cooler stars that are red in color and longer wavelength energy. So we can go over here and see that the star Spica is going to be a very hot and blue star. Whereas we go over here, we can see that Barnard star is going to be a much cooler red star. And our Sun and a star called Alpha Centauri are going to be a more medium temperature star with a yellow color. So the HR diagram is going to be used to answer questions about stars' temperature, luminosity, color, and size. So one question here is, which group of stars are the brightest? So if we're looking for brightest or most luminous, meaning the amount of energy they emit relative to the sun, of course we're going to look at the top of the chart. So our supergiants are going to be our brightest stars, and some supergiants are Spica, Rigel, Deneb, and Betelgeuse. So notice that they're not all on the left. So all these stars are very bright, but they have different temperatures and different colors because they're spread out on the x-axis. They generally line up equally on the y, but are different on the x. So you got to keep remembering, the higher it is, the more luminous, and the further to the left, the hotter it is. Alright, another thing is we can look at what group of stars are the smallest and the dimmest. So if we're looking for small stars, we're looking on the bottom of the chart, of course. And we're looking for the bottom of the chart for low luminosity too. So that brings us back to those white dwarfs. So conveniently named white dwarfs are small and not very strong compared to the supergiants, which are much brighter and much bigger, of course, hence their names. So it's important to remember that in general, larger stars are brighter than smaller stars. Now we're going to take a look at a star that's really familiar to all of us. We're going to look at our Sun on the HR diagram. And I'd like you to figure out what is the color, temperature, and luminosity of our Sun. And the Sun is right over here. So for color, we need to line up with the x-axis, temperature the same, x-axis, and for luminosity, we have to slide over to the y-axis. And we can see that our color of our Sun is going to be yellow because that's what it lines up with, this circle with the cross in it. If we want to figure out the temperature, it's right near that yellow. We have to see exactly where it lines up, and it looks like it's somewhere just short of 6,000 Kelvin, maybe around 5,800 or 5,900. And then for our luminosity, we just slide over and it's a 1. because all stars in this chart are compared to the sun. So if it's the sun, it's a number 1. Now we can use the chart to compare the sun to other stars, and we're going to use Polaris to begin. So what's the temperature and luminosity of Polaris? Be careful, because this scale over here is logarithmic. It doesn't always go up the same units. Here we're going up by ones, now we're going up by tens, here we're going up by hundreds, here we're going up by thousands. So we can see that the temperature of Polaris, again, just like our sun, they line up really well, is about 5,900 Kelvin. And the luminosity is going to be around 5,000, which is 5,000 times more luminous than our sun. So now if you think about it, well, how does Polaris compare and contrast with our sun? Well, what about temperature? Since they both line up exactly, or pretty much exactly on the x-axis, they're going to be the same in temperature. Since Polaris is much higher on the scale, it is much more luminous. It releases much more energy than our sun. And since it's also higher, it's a bigger star than our sun, and that would explain also why it's more luminous. And finally, one more question. Which star is brighter, Rigel or Betelgeuse, and which star is hotter? So we're looking at two stars here, and they both line up pretty well in terms of how high they are on our scale, but clearly Rigel is further to the left than Betelgeuse. Okay, so which star is brighter? Well, they're about the same, because they both are lining up with close to 100,000 times more luminous than our sun. But for temperature, since Rigel is further to the left, it is definitely a lot hotter than Betelgeuse, about 10,000 K or Kelvin versus Betelgeuse somewhere around 3,500 K. And that ends this lesson. We're going to be now practicing using the HR diagram when we're doing our astronomy lessons and throughout this whole unit.